known as Satisfiability Modulo theory. And today he is recognized as one of the world's experts in the development and application of SMT techniques. He was also an early pioneer in the development of formal hardware verification. For instance, at Intel, he collaborated on a novel theorem prover used to verify key microprocessor properties. And he helped build one of the first industrially successful assertion-based verification toolsets for hardware. He is an ACM distinguished scientist. And today he will talk about domain-specific reasoning with satisfiability modular theories. Please, Clark, welcome to the conference.
Great, thank you. So it's a great pleasure to be here. Too bad we can't be together in person, but this is the next best thing. All right, so, and thank you, Corina, for that introduction. Let's see. Okay, so this is a fun little slide that I share with the new PhD students every year. I tell them I'm thinking of a research area where algorithms have recently improved by many orders of magnitude. The computers can solve problems better than humans. They can solve them without help from humans. There's big investments being made by the government and by big tech, and it can be described using two letters, and the first one is A. Okay, so what research area could this be? Well, of course, it's AR, automated reasoning. So I like to just remind them there are other exciting research areas besides AI. Great, so what's AR? Well, automated reasoning is, as you know, these techniques for automatically solving constraint problems that are being used more and more in all kinds of applications, not just in verification, but in lots of other things. So it's an exciting time to be working in this field. And one of the reasons it's exciting is that the improvements in automated reasoning are really quite stunning. So just to give you a flavor, and some of you probably seen these results, this was a study that Moshe Barrett did. It's a little dated now, but if you did a similar study for the last 10 years, you'd see the same thing. So if you look at SAT solving over a 10-year period, we get this incredible speed up. So essentially, the 2012 solver is 1,000 times faster than the 2000 solver, right? So 3 orders of magnitude in a decade, and actually the results since then have been similar. We did a similar study with SMT solvers on bit vector benchmarks, and what we saw was that compared to the 2010 state of the art, the current state of the art is about 10x. But what's really interesting is this 2010 result doesn't even include 3,000 problems that timed out. And of those, all but 200 can be solved, and over 2,000 can be solved in less than a second. So we're really seeing tremendous improvements all the time in these tools, and this is continuing. So what can we do with these great tools now? Well, there's this sort of new research workflow that's emerging in a lot of application areas where you take some problem you're trying to solve, you figure out how to encode it with an automated reasoning tool, and then you hand it off to one of these solvers, a SAT solver, SMT solver, or ATP solver, and they just solve the problem for you, right? And you can read, hundreds and hundreds of papers that are instantiations of this research workflow. So this is all very great. However, what happens when this fails? Okay, so let's say you're a grad student and you're working on this problem and you figure out how to encode it as an SMT formula, and you run the SMT solver and it just times out, doesn't work, doesn't give you any feedback. So the users get frustrated when this happens. And what I've observed is they then end up spending a lot of time, well, maybe they'll try some different tools, they'll try fiddling with the options, they try lots of encodings, and even, end up writing, multiple papers about how they worked around the shortcomings of the automated reasoning tool. And some of the more unfortunate consequences is I think that they can draw some incorrect or premature conclusions about the limits of automated reasoning. And so, this leads to a stall in the research progress, problems don't get solved. And so I'd like to think a little bit about what can we do to improve this situation. And in particular, how can people developing formal methods tools, automated reasoning tools, work with their users to address this problem? So a couple of options. One, if we look at the trends, then probably if you just wait a few years, then whatever doesn't work now will work better. But of course, that's not a great option. So let's look at option 2, which is what if we could build our tools to flexibly adapt to new domains? And what I want to talk about today is essentially showing you some examples of how we can do this with satisfiability modulo theories approaches. All right, great. So that's the background. And so what I'm going to do is I'm going to give you a couple of examples of how we're able to flexibly adapt automated reasoning tools to specific domains. And I'm going to look at a couple of domains. One is verification of neural networks, and the other is reasoning about strings. And along the way, I'll try to, draw some high-level conclusions about, what's working, what's not working, where we can improve. All right, so just to give you some background on satisfiability modulo theories, or SMT. So to remind you, the problem is you're given a formula in first order logic, and you're given a theory, which you can think of as a set of axioms, or you can think of it as a set of operations with a given semantics. And then what we're going to do is we're going to try to determine whether there exists a model that models that theory that also satisfies the formula, okay? And the key enabler for this kind of flexible approach that I'm trying to talk about here is that this theory T is a parameter to the general method. So that means, T could be something very specific for a particular application domain. And moreover, SMT allows T to be a combination of several different theories. So you can add new theories and new solvers for those theories without re-implementing or changing the implementation of the existing solvers. So there's a way in which this SMT approach is inherently kind of extensible and flexible. And we're going to leverage that in the examples that I'm talking about today. All right, so then just to give you a little bit of a high level of how things work under the hood in an SMT solver. So you've got this kind of an architecture. There's a SAT solver, which reasons about the Boolean structure in the formula. And then specific theory atoms are passed to this sort of core engine, and the core engine communicates with solvers for individual theories like UF, uninterpreted functions, various versions of arithmetic theories, theories of arrays, theories of bit vectors, and so on. There's lots of different theories. Right, so the SAT solver only sees the Boolean skeleton of the problem, so everything else is abstracted away. And its job is to build a partial model by assigning truth values to the atoms. And it's just trying to satisfy the Boolean structure. The atoms that get assigned to true or false are then sent to the core as assertions. So the core then looks at the assertions coming in and hands them off to the appropriate theory. So if it's an assertion about arithmetic, it goes to the arithmetic theory. If it involves bit vector reasoning, goes to the bit vector theory, and so on. It also, sometimes the theory solvers are able to make deductions called theory propagation, and those get passed back to the core and can get passed back to the SAT solver. It also handles things like something called theory combination, because the problem is not completely modular, right? So it's not quite true that if you hand off all the assertions to the theory solvers and just ask them if those are satisfiable, then you can answer the question. There has to be a little bit of coordination among the theory solvers. They have to agree on essentially an equivalence relation on the shared variables. And so that is also handled by the core. Okay, and then finally, the theory solvers themselves, they just have the job of deciding the satisfiability in their theory of the literals that they see. And then to be efficient, they should also be incremental and backtrackable. And then they have to be able to do conflict generation. Once they see something is unsatisfiable, they have to give back a small subset of the assertions that are unsatisfiable. Okay, and then you put all these pieces together and you get yourself an SMT solver. Great, so let's move on to talking about how can we do this sort of domain-specific reasoning and adaptation within this larger SMT framework. All right, so first I'm going to talk about this application to verifying neural networks. And this is joint work with several of my colleagues at Stanford. And in particular, Michael Kokendorfer, who's the third one pictured here, actually got me started by approaching me with this interesting problem. So I'll tell you the problem. So he's a professor in aeronautical astroengineering. And essentially he said, hey, we're looking at developing a new airborne collision avoidance system called ACAS-XU for drones. And essentially the way it works is well, the way the collision avoidance systems work in general is if you're on an aircraft and there's an intruder aircraft, then you have some information about, the distance and the angle and the relative velocities and so on. And that information gets fed into some algorithm that's supposed to produce an advisory, which either tells you you're clear of conflict, you can keep flying, or you should go left, right, or strong right. So that's the job of these ACAS systems, is to monitor the airspace. And if you're in danger of a near midair collision, then it gives you an advisory to steer you away. Now, they had an algorithm for there's a standard algorithm for this that was actually developed by Professor Kokendorfer. But the version for drones, they had the problem that the standard algorithm requires many gigabytes of memory. So they wanted to do something that had a much smaller footprint for drones. And they came up with an idea to use a series of neural networks. And actually it works pretty well. But of course, everyone's worried about putting neural networks in a safety critical system like this, because can you trust it? So he came to me and said, hey, could you verify a neural network? And I said, well, what's a neural network? And then he explained it. And I said, oh, great. So it's actually just a bunch of linear algebra. So a neural network looks like this, right? You've got some inputs. They go through various layers. At each layer, you do some weighted sums, which is just linear arithmetic. And then on the output of each layer, you typically have some additional computation, which is called an activation function. Okay, so far so good. What is this activation function? Well, a common one is a very simple function called the rectified linear unit, or ReLU. And it just takes the maximum of the value coming out of that node and 0, okay? So the idea is if the value coming in is negative, then it gets ignored. So that's called an inactive state. And if the value is positive, it just gets passed through, and that's the active state. However, this ReLU introduces a nonlinearity. And in fact, this makes reasoning about these neural networks NP complete. Okay, so what can we do? How can we reason about this? How can you verify a neural network? Well, let's look at a simple example. So here we have a single input, and then there's a weighted sum to a hidden layer with 2 neurons, very simple, and then an output that combines those 2, okay? And so we can write just 3 equations to describe this network. we would say that x2, the value in x2 is the result of applying the ReLU function to 1 times x1. And the value x3 is the result of applying the ReLU function to -1 times x1. And then x4 is just the sum of x2 and x3. Okay, so that completely describes this network. And furthermore, if we're using standard SMT logic, we can actually encode this ReLU in an easy way using this if then else statement, or ITE. So it just says if this input 1 times x1 is greater than 0, then we pass it through 1 times x1, otherwise 0. So we're just implementing the max function using if then else, and same thing for the other value. All right, so that's great. So we can actually encode a neural network with a ReLU function, with ReLU activation functions in an SMT formula pretty easily. So for the ACAS-XU networks, there are about 300 ReLUs, which give us 300 instances of this if then else operator. And the first thing we tried was we just tried feeding this into our SMT solver. And disappointingly, the SMT solver was not able to do anything very smart. So essentially what it ended up doing is just splitting on all of these conditions in the if then else's, which meant that we were essentially exploring a space of size 2 to the 300, which is very large. You can't hope to explore that space in the lifetime of the universe. So that's not great. We also tried encoding this using a standard mixed integer linear program encoding, and this also just didn't work at all. Okay, so we were, we had applied this workflow where we found a problem, we encoded it using automated reasoning tools, and it didn't work, right? This is exactly the scenario I was talking about before, what happens when this fails. Okay, so luckily, we're not afraid of changing our solvers or extending them. And SMT gives you a nice way to do this. So the first sort of observation we made is, well, this ReLU function, encoding it as an if then else means that we don't have the opportunity to reason about it in the theory solver. Instead, it's being handled by essentially the SAT solver, right? By doing these splits. And what if we instead extend the theory solver to include this notion of a rectified linear unit? Then what we would have to do is take our theory solver and somehow extend the algorithm to understand this operator. Okay, now these are exactly the right questions to ask. What happens if you extend the theory, and can you extend the algorithm? But these are the research directions that are often avoided because solvers are treated as black boxes. And so one, I think, really important research challenge is how can we make changing or adapting these solvers less formidable? I'm not going to answer that question today. So it's not too formidable for those of us who develop solvers, but it would be great if more people were able to change them. All right, so now I'm going to give you a little bit of a dive into the Simplex Solver so we can understand how it works and how to adapt it. I'm going to give you a calculus for Simplex at kind of a high level. So the idea is you have some arithmetic variables, x1 to xn, and a particular Simplex configuration is a tuple with 5 parts. So the first part is just some subset of the variables that we're going to call basic variables. Okay, B is the set of basic variables. Then we have this tableau, T, and essentially the tableau is a set of linear equations. And it just says for each variable in the basic set of variables, you have an equation where you can describe that variable in terms of a linear sum of the non-basic variables, okay? So you can think of it as the rows. So the tableau is sort of a matrix where the rows are basic variables and the columns are non-basic variables. And you have an equation that relates each basic variable to a weighted sum of the non-basic variables. All right, so then you have, for each variable, you have lower and upper bounds, okay, which could be infinity or negative infinity, but those are the bounds on the variables. And finally, alpha is a current assignment. And this just tells you your best guess right now as to what the values of those variables should be. Okay, so this is your configuration, and then the steps in the algorithm are going to modify this configuration. Now, to start with, we have to generate an initial configuration. And the way we'll do that is every time we get an input, okay, and an input is going to be some linear constraint, some weighted sum of variables, which is either equal, less than or equal, greater than or equal to some constant. So what we'll do is basically, let's see, we'll pick some variable and add it to the basic. We'll add the equation to the tableau, and then we add this, this D, this constant, to either the lower or upper bound, depending on whether this is less than or equal or greater than or equal. And then finally, our initial assignment will just be, let's assign all the variables to be 0. Okay, so basically you can take each of these constraints in your input, you can translate it into an equation in the tableau, plus a constraint on the variable, and then we're ready to go. Okay, so how does the algorithm work? So basically the algorithm works by, so we have an invariant that says the non-basic variables should always be within their bounds, but the basic variables are allowed to violate their bounds. And your goal is once you have all the variables within bounds, you're done. We're just trying to find a feasible solution here. Okay, so the way we've constructed the formula, we're guaranteed that the constraints are on the basic variables. So what we're going to do is we're going to look for a basic variable that's violating its bound. So what this pivot 1 rule says is you have alpha at xi, that's the current assignment of xi, is less than its lower bound. Okay, so it's out of bounds. And furthermore, there's some xj, which is a non-basic variable that has some slack. Now, what do I mean by slack? Well, slack just means that it's less than its upper bound and its coefficient is positive, or it's greater than its lower bound and its coefficient is negative. So in this linear equation that relates xi and xj, there's xj can move in the direction that xi needs to move in order to no longer be violating its lower bound. But we're not allowed to change basic variables directly. So first what we do is this pivot operation where we essentially switch one basic variable with one non-basic variable. And what the pivot operation does is it just solves for xj in the equation and then substitutes the solved value in all of the rest of the tableau wherever xj appears. Okay, so this is like just some basic linear algebra. And then that allows you to change this xi. And there's a similar rule pivot 2 for when a variable is above its upper bound, and a similar definition of slack there. But all of this is to set up this update rule. And the update rule says if I have a non-basic variable that's, then I can move it essentially, and there's some slack in it, so it's less than its lower bound or above its upper bound, then I can move it towards either its lower or its upper bound. Okay, so that's great. Good. So this is an abstract representation of the way the simplex algorithm actually works. And of course, in practice, you have to have strategies about how you pick these variables I and j, which are called the leaving variable and the entering variable. And there's various, optimizations and tricks here. But essentially what happens is you repeatedly do this until all the variables are in bounds, or which is this success rule, okay? Or you get to a point where you have an out of bounds basic rule and there's no slack. And it turns out that if you have an out of bounds basic variable and no slack in that row, then that guarantees there's no solution. Okay, you can prove that. And so if we get to that case, then we know the whole thing is unsatisfiable. And it turns out that this calculus is sound and complete. And if you use the right strategy for choosing variables, it's also always terminating. Okay, so great. That's just there's lots more that could be said about that, but that's just the way we're going to think about the simplex calculus. Now, what we're going to do is we're going to extend this calculus so that it can also reason about these ReLU connections. So we have this tuple as before, the 5 parts of the tuple, but we've added a new part called R. And R is just some set of pairs of variables, and it's going to represent ReLU connections, okay? So the way we're going to now set up our initial configuration is basically if for atoms that are not about ReLUs, we do the same thing as before. But if we have an input atom that says xi equals ReLU of xj, then we add xi, xj to this ReLU connections set of pairs. Now, what can we do once we've done that? Well, we add a new rule called update, update sub b, which means update the backwards facing variable in a ReLU. And essentially what happens here is if I have a ReLU, okay, xi, xj, and the current assignment does not satisfy the ReLU function, so xj is not equal to ReLU of xi, and furthermore, the xj, which is the output of the ReLU, is positive or non-negative, then we can update the input of that ReLU to be the same value as the output. So we'll update it by an amount that's xj minus xi in order to make xi equal to xj. Now, after you do this update, this ReLU function will be satisfied, okay? So this is just a little rule that allows you to satisfy a broken ReLU constraint. And similarly, now this one you can only apply when the output is non-negative, but the other one, the update f, you can apply always. And essentially here, what you're going to do is instead of changing the backward variable, you're going to change the forward variable with the xj variable, and you just make it equal to whatever the output of the ReLU should be. So it's either equal to xi if it's positive, or it's 0 if xi is negative. Okay, so the update f rule always applies. The update b rule applies whenever the output is positive. And then, of course, we still want to keep this invariant that only the non-basic variables can be changed. So we have this pivot rule that allows us, if we have a variable that participates in a ReLU constraint and it's a basic variable, then we're allowed to pivot it. And then finally, we also have this rule called Relu Split. And what this does is it basically allows you to split whether a ReLU is in the active or inactive phase, and then consider only that direction. But you do have to consider 2 cases. And then finally, the success rule now says that all of the variables have to be within their bounds and all of the ReLU constraints have to be satisfied. Okay, so now what we've done is we've taken the simplex calculus and we've extended it with some new rules. So let's see how this works in a simple example again. So here's our simple network, and suppose we want to ask the question, is it possible for the input to be within the range 0, 1, and the output to be within the range 1/2 to 1? Is that satisfiable? Okay, so the first thing we're going to do is we're going to split these internal nodes, the ones that have the activation functions. We're going to split them into 2 variables. We have the incoming variable and the outgoing variable. Now we can write a bunch of constraints. Okay, so we write these constraints on x5, x6, x7. Those are just going to represent these different terms. Then we have bounds. Okay, so the bound on x1 is 0. We got that from our initial condition, right? And then the upper bound on x4 is 0.5, and the upper bound on x1 is 1. Okay, and then we have this, sorry, the lower bound on x4 is 1/2, and the upper bound on both the input and output are 1. That was what was given to us. But then we also add these ReLU constraints that say, okay, there's a ReLU on x2w and x2a, and x3w and x3a, And we start with the assignment where everything's 0. So our basic variables here are this x5, x6, x7 that we introduce. And then our lower and upper bounds are given here. And the lower bound and upper bounds on the basic variables are all 0. Okay, so let's look at so here's a little visualization of what this looks like. Our tableau is these 3 equations. And then we have these variables and these bounds, lower and upper, and the current assignment. So if you look at this, everything's good except that x4 is out of bounds, okay? So we have to update x4. So we're gonna add 0.5 to x4, so that's great. Except then that's gonna change x7 because of the equation that x7 depends on x4. So x7 is a basic variable. Okay, so now x7 is out of bounds. So how do we update that? Well, first we have to pivot it. So we pivot with x2a, and now we can update x7 and bring it to 0, which is within bounds. But that implies that x2a is 0.5. All right, so now notice that x2a is part of a ReLU constraint. So what are we going to do? We're going to use the ReLU update to update its corresponding output, its corresponding input, x2w. So we update x2w to be 0.5 so that ReLU constraint is fixed. And now x5 becomes 0.5 because of the first equation. So now we have to update x5. So let's pivot it. We pivot it with x5, and now we pivot with x6, and so now we can update x5, so it's 0, which implies changes for x1 and x6. X1's okay, but x6 needs to be fixed, so we pivot and update that, and now x6 is 0. Which changes x3w, but notice x3w being negative is fine because the output is 0, and that's exactly what it is. So now actually we finally reached this ReLU success. So all of the variables are within their bounds and the ReLU constraints are satisfied. Okay, so notice that what we did here is different from what the naive SMT encoding would have done. So the naive SMT encoding would have introduced 2 if then else's for these ReLUs, and it would have split on those first. We did this whole thing without any case splitting at all. We just did a bunch of derivations and then eventually found a successful assignment. So let's look at what we know about this calculus. So it's sound. All of these rules can't introduce an inconsistency, so that's great. But does it terminate? So is it always possible to find a solution with pivots and updates? So the original simplex calculus does have this nice property that it is always possible. But for our extended calculus, we don't think it does have this property, which is not surprising because the problem is NP complete. So how does that manifest? Sometimes you can get into a loop. Essentially what happens is you fix a ReLU constraint, you do some pivots, some updates, and you come back and you have to fix that same ReLU constraint again. And this could happen over and over. So how do you avoid this problem? So what we can do is we can use this Relu split rule to break loops, and we can apply the rule lazily. So essentially we'll count how many times we apply these update F and update B rules. These are the rules that update the Relu constraints. And if our count exceeds some threshold, then we'll decide that that's a problematic ReLU and we'll split on it. Now, in the worst case, if you split on every ReLU, that just reduces to the problem we had initially of representing things as if and else's. But if we don't have to split on everything, then this might buy us some improvement. And in fact, when we implemented this and tried it on these ACAS XU networks, we only had to split about 10% of the time. So then we went from 2 to the 300 down to 2 to the 30. and 2 to the 30 splits is quite manageable by an SMT solver. And so then we were able to solve these problems. Okay, so that's a little introduction to how we got into the business of verifying neural networks. And what I want to emphasize here is this sort of interesting way that we tried it with a regular automated reasoning tool. It didn't work. And so then, the thing to do was to flexibly adapt the tool to the domain by finding a way to reason about the Relu constraint directly. And there's lots more you can read about this work and also lots of follow-on work. So this was a paper in CAV 2017. We have a neural network verification tool called MEMOCODE that you can find. We wrote about it in this paper, and also you can find it on GitHub. And there's beginning to be a fairly active community in this area. For example, there's a workshop associated with CAV called Formal Methods for ML-Enabled Autonomous Systems, or FOMLS. And there's also been a yearly verification of neural networks competition. Great. So that was the first thing I wanted to tell you about. So let's move on to another example. And this is joint work with a number of people, David Brumley's group at CMU, some students at back at NYU, and also at University of Iowa and at Stanford. So a lot of people working on this problem. And here's the motivation for this problem. The initial motivation we had is symbolic execution. So as you probably know, symbolic execution is a technique where you maybe want to enumerate the program paths in a particular program that end in some particular target state, maybe a bad state, could be a security violation or some other kind of problem. And then what you can do is you represent the program inputs as variables and translate the statements along the path into constraints on the variables. So then these constraints represent all possible executions along that path. And solving the constraints determines whether the path is feasible. If you do this for all of the paths, you can check whether any particular program point is reachable. Okay, and this is a very powerful technique. It's been used in a lot of different ways. One of the big success stories of symbolic execution was the Sage tool at Microsoft, which they claimed, at some point had found 1/3 of all the bugs that were found in Windows or something like that. So anyway, this is an established technique. And in particular, it can be used to search for security vulnerabilities. So here, what you do is you take a particular security policy and some code. You translate this into a symbolic execution problem where you get a formula that's satisfiable if and only if the code violates the security policy. And then the solver checks to see whether it exists or not. And what we were interested in initially in this project is there are a lot of times, you have to reason about string manipulation because a lot of these security attacks involve, doing tricky things with strings that are passed in through the input. So the problem that we had when we started working on this is that essentially, if you encode strings in the way that programs reason about them, which is as a series of bytes, then you have to reason about this sort of low-level representation about strings. You also have to fix the maximum lengths of the strings, and certain high-level operations like length turn into loops, which are hard to reason about. So the idea was, okay, let's adapt to this domain where we're trying to reason about strings. Let's define a theory of strings and a calculus for reasoning in this theory. So just to show you a little bit how this works, we're going to pick, say we have some alphabet, which is a finite set of characters. It could be, ASCII, or it could be something else, but let's say it's the ASCII characters. And then we have some constants in the theory. So we have the empty string, and then we have a character, the character string, which is a set of strings for each character in the alphabet, okay? Then we have operators like length that gives you the length of a string. You can concatenate two strings. You can ask whether they're equal. and you can ask whether a string is in some regular expression. Okay, so this seems like a nice language that ought to be able to represent lots of the kinds of things that we want to do with strings in real programs. Now, of course, there's a problem, which is this language is known to have some difficult complexity. So in particular, if you just take concatenation and equality on strings, then this reduces to what's called the word equations problem. And it's known to be decidable in p space, but it's you know, a hard problem, known hard problem. If you then add length, this actually is unknown whether this is decidable. And then if you add just some small amount of high-level reasoning, like replace all instances of a substring, it quickly can become undecidable. Okay, so what do? Well, we take a pragmatic approach. So we're going to create a rule-based calculus that we believe will work well in practice. We're going to leverage our existing arithmetic solver to reason about length and constraints about length, so we don't have to do that twice. And then we just sort of embrace the fact that our calculus may be incomplete, right? So we're not going to try to prove completeness when it's, you know, could be a hard open problem or even undecidable. What we're going to work for is something that works well in practice. And this is actually in line with, you know, other sort of attitudes in automated reasoning today. You know, we're not afraid of tackling NP-complete problems or even piece-based problems, because what we've discovered is that in practice, often you can solve these problems, even though their worst case may be very hard. That's sort of behind why SAT solvers are so successful. You know, they still are NP-complete problems, but in practice, they often can be solved efficiently because there's some structure and some, you know, strategies that work on real world problems. So that's what we're hoping for here, is that for these real world string problems, a similar approach will work. Okay, so here's a little example for you of how you might do some rule-based reasoning about strings. So let's say we have strings X and Y. And remember, one of the key things that we want, properties we want, is we don't want to fix the length of X and Y. So X and Y could be any length. But we have this length operator, which I'm representing with the two bars here. So the length of X is equal to the length of Y. X is not empty. There's some other string called Z, which is not empty. And then the concatenation of X plus some constant C1 and Y is equal to the concatenation of Y and C2 and Z, where C1 and C2 are different characters, okay, in the alphabet. So how would we reason about this set of constraints? So we have a rule called len, which says if I have two strings that are equal, then their length has to be equal. Okay, so this last constraint tells us that these two lengths are equal. Then we can do this length split that says, well, a string is either empty or it's not empty. So we'll do that for Y. And if we consider the first case where Y is empty, if Y is empty, we can conclude that its length is 0. But we know that X is not empty, and that the length of X is greater than 0. So if length of X equals length of Y, that leads to a conflict. Great. So we know that Y can't be empty. So that's case 2. So if Y is not empty, we can do this F unify rule that says, basically it looks at this equality between two concatenated terms, and it says that means that the first two terms here have to be equal because their length is the same and they appear in the beginning of a concatenation, so they have to be equal. Now, if X equals Y, we can normalize the last equation to have X as the first position on both sides. And then that same rule says, well, that means that C1 has to equal C2, and that's a conflict because these are different characters in the alphabet. All right, so that's just a flavor. There's lots more rules I'm not going to go into, but essentially you can build a little calculus that lets you reason about these things. All right, so we did that. And then, you know, our users working on the application said, well, that's great, but I actually need more operators in my real programming language. So we said, okay, we can do that because SMT is adaptable. So let's extend the theory. Let's add some new operators. And we'll implement them by reducing them to the core theory that we already have. So we can implement things like substring, string containment, index of, and replace. This is not replace all, this is just replacing the first occurrence. So this doesn't trigger that undecidability. Okay, so these are the operators. And maybe just in a little more detail, substring takes the maximal substring of X starting at position N with length at most N. Contains XY is true if X contains a substring that is Y. Index of gives us the first occurrence of Y in X looking starting from position N. And replace is replacing the first occurrence of X in Y by Z. Okay, so this shows us how you can reduce these to the core theory. I'm not going to go through all of these in detail, but maybe just look at the second one, contains. So Y contains Z if there exists some K bounded between 0 and the length of Y minus the length of Z, such that if you look at the substring starting from K of length Z, then it's equal to Z itself. Okay, so basically you can think of this as it's sort of a bounded search. It's going to search for Z and Y at every position, starting at position 0 up to position length of Y minus length of Z. So this is the only one that introduces a quantifier. The other ones you can do with if and else's. Great, so this gives us a nice, easy way to extend the theory with new operators without having to change our implementation much at all. We just have to implement these as rewrite rules. All right, well, okay. Unfortunately, that's too slow. So what happens is if you have some non-trivial string problems, then these reductions introduce lots of K-splits or quantifiers, and that ends up being challenging, and it ends up blowing the problem up. Okay, well, we can do better. So remember in the neural network case, we actually extended our solver as well to reason directly about new operators. We can do that here too. And there's kind of a clever trick that we can do, which is basically we'll keep these formulas with the original operators. And rather than trying to come up with a calculus that's complete that reasons about these operators, we'll just periodically try to simplify them. And you know, if we're successful, we can simplify the difficult operators away. And if not, then eventually we can reduce them to the core theory like we did before. So the key here is to build a really strong simplifier. And let's see about some examples of how we can do this. So just looking at some examples using the contains operator. So here we could say so here L is going to represent a string literal, which is a sequence of characters from the alphabet. So if I have two string literals, I can just check to see if one of them contains the other. So that's easy. If I have L1 contains some string literal concatenated with T, then if L1 does not contain L2, then it's already has to be false. Similarly, if it already contains L2, sorry, if you just take out the L2 part and you can show that that doesn't work, then it doesn't contain L2 concatenated with T. Okay, so there's some more rules here. I won't go through all of them. But basically what you're going to do is you're going to look at just some common cases that occur in real problems, which are these simple kinds of contains questions. Often they have some string literals in them because, you know, there's some string constants that appear in the program. And so many of these you can just reduce to true or false, or you can simplify them to some simpler contains query. Okay. Good. So what this allows us to do, basically what you can think, the way we did this work and the way we wrote these papers is we were looking at, benchmarks from real symbolic execution queries, and we just kept finding more things in them that were hard. And then we were able to come up with more and more techniques to make those easy. And this is a common theme in SMT work, is that if you look at your real application, you look at what's hard about the benchmarks, then you can often extend the theory, extend the solver, add new tricks to make it work. All right, so that worked pretty well, but some of the problems were still too hard for these basic kinds of simplifications to work. And so we can do something even smarter. We can sort of supercharge the simplifier by building a mini inference engine to derive even more simplifications. So let me show you how this works. So essentially here, what we're going to do is we're going to add this little inference engine that lets us deduce more stuff about string length. So for example, if I know that the size of T is greater than or equal to the size of S plus 1, so T is bigger than S, then any equality between T and S has to be false. Similarly, if I know that size of S plus size of Q is at least as big as T, then if I have T as a concatenation that involves something else like R, then S and Q already take up as much space as T has, so R has to be empty. So we can figure out that R is empty. In some cases, we can reduce a contains to an equality if we know that the size of S is at least as big as the size of T, right? Then this can only be true if T equals S. For substrings, we can just essentially check if we know that V is out of bounds, or W is out of bounds, then the substring operator reduces to the empty string. Okay, and so on. So there's more tricks we can do. And basically, by having a really strong inference engine about the string lengths, there's a lot of reductions you can do on these complicated operators. Okay, now, one thing you might be thinking, and this is a fair question, is, well, okay, so you've done all of this extra work, and now aren't you in danger of really overfitting to this one symbolic execution domain? So you might worry about that. Of course, we do worry about things like that. And then what's cool is we actually had sort of out of the blue, a completely different application pop up where they were able to use this string solver. So the Amazon Automated Reasoning Group is using this string solver to do something completely different. They're using it to check access control policies for the cloud. And they sort of informed us that they were calling it a few million times per day. So how does this work? So they have a tool called Zelkova. And the way this works is they'll take an access policy, and then they'll take a question of whether an access policy is stronger than another access policy and reduce that into an SMT encoding, and then call either CVC5 or Z3, which are the two SMT solvers, two SMT solvers that support strings. And then they can use this to answer questions like, did you just create a policy that's actually no better than the public policy? Did you just make all the data public? And they can, inform their customers, when they make mistakes like that. So this is a really important tool for Amazon, and they're using our string solver. Okay, but which shows that, if you build a nice general solver for one domain, then often it can work in another domain as well. So that's great. However, they did, of course, have some requests. And one of the things was that they were using a lot of regular expressions. And for regular expression reasoning, we were still kind of using a very naive reduction to the core theory. So I'll just show you one more trick here for regular expressions. So this is an example of something that that comes up where you have X is in this language where you have 0 or more digits followed by A, then a bunch of stuff followed by B, and then some other stuff. And then you also have a constraint that says X is not in the language of 0 or more digits followed by A, followed by some other stuff. Now it's clear that these are inconsistent because this first language is a sublanguage of the second language. But the sort of standard thing to do is to do some kind of automata-based approach. And if you do that, you have to reason about complement and intersection, and those are quite expensive, okay? So we want to do something a little bit different. So we're going to do a word-based approach. And in our word-based approach, we translate an equation like this first one into an inequality that says X is the concatenation of these different parts, okay? But we still have to say that X1 is in, it has a regular language constraint. And the problem is that this leads to a non-terminating sequence of unfoldings, okay? Because for this X1, we have to expand that out again into another sequence, which could be expanded further. Now this does work in some cases, but for the case here, it's not gonna work. And so you can, again, sort of look at the kinds of problems that come up in practice and find novel solutions. So an example of what we can do here is we again build a little mini inference engine that can reason about language containment. All right, so basically it works with a bunch of rules which are fairly straightforward. Things like, you know, the empty language is a subset of anything. Anything is a subset of the full language. Language containment is transitive, and so on. And just some other little tricks here. And this actually allows us to deduce that this first language is a sublanguage of the second one in 2 steps.
Clark, sorry to interrupt. You have 3 minutes left if you want to.
Yep. I think this is my last slide, so we're just almost there. Okay, great. So anyway, this is what we did with our string solver. There's a lot of papers here that you can read. There's a nice paper about Amazon's Zelkova tool, and you can check out our CVC5 SMT solver on GitHub. Okay, so to conclude, what I hope I've left you with is this idea about domain-specific reasoning, which is, well, first of all, collaborations with other users in industry are great ways to discover new domains that may be challenging. And by having this idea that we can adapt AR solvers to new domains, we can break through these workflow bottlenecks. And this SMT paradigm really seems to be a sweet spot because it provides both generality and flexibility. So generality meaning, you know, you develop a solver for one domain and it works in other domains. And then flexibility meaning it's easy to extend the solver, relatively easy. It has, you know, we know how to do it. There's still this big challenge, which I think is a challenge that we need to think hard about, is how do we make it easier for non-experts to adapt and customize these SMT solvers? So we have some ideas in that direction, but I think this is still a big challenge. And just one you know, interesting current challenge we're working on, collaboration with industry, smart contract verification, working with both Facebook and Certora, a couple of companies doing smart contract verification. And they, you know, they have different kinds of challenges, especially large bit vectors, right? 256 bit vectors. And, you know, the standard techniques don't work. And so once again, we have the opportunity to create domain-specific solutions, which hopefully will generalize for many other users. Right, and I'll conclude there, and thank you for your attention.
Thank you very much for the very nice talk. Let me send you my applauses on behalf of the audience. So it's 10 a.m. Pacific time, so technically, yeah, our time slot ended, but perhaps we have time for one question. So there are some questions on chat. I'll start with the first one. This comes from Joseph Scott. Hi, Professor Barrett. I'm Joseph Scott, a PhD student at the University of Waterloo. I enjoyed your talk very much. It appears several performant VNN lib solvers from VNN FM'21 were built upon MILP solvers such as Gurobi and so on. However, these tools are often bundled with other techniques, for instance, incomplete solvers, abstract interpretation, and so on. So then here comes the question, I hope. Firstly, in your talk, you made a clear case for a more lazy approach. Sorry. Okay.
Yeah, but actually I scanned this. Maybe I can just address.
Summarize and address, please. And then he also challenges the AR, isn't AR part of AI? So yes, please comment.
Yeah, maybe answer the last one first. So
okay.
back when I took AI, it was, right? But these days, AI means machine learning. So I think, you know, in the big umbrella, it's true, but in practice, the way research is done today, it's not. And I think it's a really interesting question of how we can bring these two fields together, because they both have, you know, tremendous strengths, and I think they're complementary. Yeah, so just maybe a couple words about MILP solvers and neural network verification. So, you know, the story I told you today is sort of the beginning of the story, and there's been many more chapters since the beginning. And I can't, you know, go into all the details. There's tons and tons of work in this area. So it is true that the current sort of best techniques involve a bunch of pre-processing and then running an MILP solver. But a couple of things that are worthy of noting. I believe Gurobi actually, you know, read our paper and did something to make their solver much better at these ReLU-based sets of constraints, because, you know, the earlier versions did not handle it as well. So hopefully we influenced them a little bit. Or if we didn't, they just, you know, did it on their own. But in any case, you know, they've adapted their solver. So that's an example where they've adapted something to improve this application area. And I think the other reason is, you know, these industrial commercial solvers for linear arithmetic, they have, you know, decades of really advanced techniques that nobody understands that's not in that field. So it's hard for, you know, an academic tool to compete with that. But I think ultimately there should be some kind of, you know, more work done in those solvers, maybe make them more lazy or something. I think that's what we learned from this experiment.
I see. Thank you very much. So I guess you can continue talking to the audience on Wonder Me. If you can please join that
Sure.
After the talk. And there is another quick question perhaps from Dominique Marie. Thank you for the very interesting talk. I did not know the use of CVC5 tool and the use of strings for reasoning over those problems. Okay, so this is a thank you note. I also want to thank you very much. I just wanted to ask in the end, so what is the lesson learned if I want to adapt or not me, but somebody would like to adapt an SMT tool to a new domain? Is there a general lesson learned, or it's really domain specific? Yes. Please.
I think the current answer is please talk to us, right? If you run into one of these bottlenecks, because it means there's an interesting research problem, and we'd love to collaborate with you on that. Now, long term, it would be great if it can be easier for a non-expert to do it, but we're not there yet.
Okay, great. Thank you very much. So on this high note, we would like to thank you again for the nice presentation. And this concludes the first day of FM. Bye.